Hello and welcome to all the viewers. In this video, we will going to discuss about cell phone, that is smartphone drop test analysis using ANSYS Workbench. So this slide represents the learnings in this video. So very first, we will going to discuss about how to assign a different material for the respective cell phone, then how to perform the meshing, how to apply boundary and loading condition. Then we will discuss about how to extract the results, like how to extract one message stress, then your principal stresses, as well as few other parameters which are required for explicit simulation. In addition to that, we will also going to discuss about how to set up the front edge drop as well as front face drop simulation. So this slide represent our actual problem statements. So here we need to perform the drop test, that is explicit dynamic simulation of a cell phone. Okay, and here we need to perform corner drop, front face as well as front edge drop simulation. So here we can assume that the drop height of 1.5 meter, or else you can assume whatever the velocity like 15 to 20 meter per second, or here for specifically for corner drop, let's assume 22 meter per second velocity. I will tell you how to calculate this drop height. There are two options. Either you can define the respective drop height, or else you can calculate the your initial velocity by using let's see, as we know that our kinematic velocity is 1/2 mv square is equal to let's say the inertia mgh. So here if we subtract this, then we'll get the velocity is equal to square root of this 2 will come over here, 2, then your gravitational acceleration, and then your respective height. So this height you can consider like 1.5 or whatever your height is. Right now we are assuming that it is dropping from your front pocket. Okay, so accordingly you can calculate the respective velocity, and then you can apply this velocity in a space clear, also in a ANSYS mechanical. Okay, and also you will find that the distance between these two also, you can convert that respective distance into the respective velocity and add over here, and then you can perform the simulation. So basically make sure that this distance should be as minimum as possible, so that your simulation time will drastically reduce. Okay, now let's see here, there are different materials which we need to assume, like the front glass. In actual, the front glass should be tempered glass, but at present we are just assuming that is a float glass, which is not the realistic one. But let's assume a float glass for this your front face. Then your body cover, that is polyethylene, this body cover, that is a plastic. Then your body, so inside body is nothing but your aluminum alloy, and this bottom platform, which is nothing but your rigid platform, let's assume as a structural steel. So what we will do now, we will go to our ANSYS, and there I will going to discuss how to set up this respective problem definition, how to apply boundary condition loading, as well as how to perform the meshing. So now we are in our ANSYS Workbench. Once you will open your ANSYS Workbench, you will find this project schematic, from where you can simply drag and drop, like here explicit dynamic. So you first need to look where this is explicit dynamic, so you just drag and drop like that, and then you can create your respective deck. I had already solved all three different load cases, as it will take time to perform the solution. So now in front of you I created one more deck. So here first you can go to the geometry in order to see what are the geometry aspects. So if you see, Now you can see this is what your geometry looks like. Here this is nothing but your toughened glass. Let us hide. Uh, this is what your body cover. So you can right click and hide. This is what your actual body of the, and then bottom is a platform. So basically this is nothing but your simplified geometry of a cell phone. You can change according to your preference, or you can even model the actual model. Okay, so once you have imported that model, you can simply do the changes according to your convenience, like you can change the height. Right now your solution time basically based on your distance of this object to travel. So basically you can do one thing, you can move this object as closer as this platform so that your simulation time will going to reduce, and do that changes into the equivalent velocity. Okay, now let's do one thing, let's go to our mechanical. So you just double click here, and here let's start the building the solution day. So very first we need to create the geometry. By default you will find the structural steel as a material, but in actual, if we can see over this, there are different four materials like aluminum alloy, polyethylene, float glass. Let's go to workbench, double click over engineering data. So here you need to click to engineering data sources. So now we are referring data from the ANSYS library. So here you can go to see explicit materials, and under the explicit material you will find the different types of material from where you need to choose your component materials. So now structural steel, you can see the outline of favorites. So here there are different materials will going to be displayed. So now it is searching for the respective materials. Now you can see here you can either choose aluminum alloy, or you can even check this one. This is also one of the aluminum alloy, you can consider that, right? So you need to click in order to consider, so that you will find this book symbol. It means it is added in the library. Okay, now if you go down you will find uh, so the glass, for the glass you should, in actual you should use the tempered glass. Just find out the respective material for tempered glass, but for the simulation purpose I am just using these float glass. This is not the correct one, but in order to show you how to you can define the respective material. So that is float glass, and then we can use the another material, that is polyethylene, that is a plastic. So let's look into plastic. Polyrubber is there, polyethylene is there, so we can use polyethylene. There are different plastic materials like polycarb, ethylene, polyrubber, polystyrene, polyurethane. So out of this let's use polyethylene. Okay, and here if you see down you will also come to know what are the different details it may includes, like it is shock US linear properties are there. Let's talk about the aluminum alloy. This is for float glass. You will find the Johnson strength continuous model is there, polynomials US model is there, and for the aluminum alloy you will also found the different material like stress strain curve, which is already defined, and shock model. You can even model by using the bilinear material. Okay, like that also you can use that. For that let's see, go to general material, and here you will find aluminum alloy, right? So you can even use this aluminum alloy and define the respective bilinear details. Okay, I will show you that also in one of my model. So now you can see this is ANSYS or illustrated is there. So let's go to here. I think I had defined. So if you see here aluminum alloy, so you can see here by linear isotropic hardening. So basically you need to define the yield strength and tangent modulus. So that can be defined from your respective toolboxes. So here you can define by linear iso. You need to double click over here and enter this constant. Okay. So this is all about your material definition. Once you have added your material, right click, go to your directory. You need to first refresh and then you can go inside your mechanical. So now once you open your mechanical, you need to assign the respective material to the respective component. So let's see the first component, that is corresponding bodies and tools. So this is nothing but your glass. So let's assume float glass. Okay, you can see your changes over here. The next is nothing but your body cover. For this, let's assume as a polyethylene. Then next will be your platform, that is a structural steel. And here for the structural steel, once you will use, you can see over here the stiffness behavior we consider as a rigid. So you need to change from flexible to rigid. Now let's see the other component, that is the inside one, that is a body. This body, let's consider this as a aluminum alloy. Okay, so these are the all four components, and if you wanted to see, you can change even this body color according to the display tile, according to the body color, part color, material stiffness. So like that there are different options are there. At present we will consider as a body color. So this is the first step of defining material, and then the next step is you need to define the connections. So under the connections you can always see the body interaction is there. By default for all bodies it is a frictionless, but in our case these components should be glued to each other. So for that, let's select all these components, right click, insert body interactions, and under this you can assume as a bonded. Okay, so what we are using, we are defining all these three components as a definition of bonded. So it is as same as your bonded contact. Okay, and then let's define this face. Let's define insert joint, and here you can define this as a fixed joint. Okay, so you can see over here all degrees of freedom are locked. So basically either you can define this fixed joint, or else you can even define the fixed support at the bottom. Okay, so let's make it body to ground, select this face, apply. Okay, so what we did, we use a fixed joint body to ground and selected this face and defined all degrees of freedom are locked. So now the connections are defined. Now the next step is to perform the meshing. So for this, let's assume a meshing size of 3, or even you can go with the 4 also. So let's try to, we are giving, this is nothing but your global mesh. For local mesh, you can select the respective component, insert, method, and sizing. So like this you can define the respective sizing for each and every component. Like for this sizing, let's hide. For this also insert sizing. So basically you can here define sizing for each and every component. So let's assume like show all bodies here. This is, you can rename, and you can even define body cover, like that you can do. Okay, here rename based on definition. So basically instead of defining name over here, you can even define the name over here. Like let's do here or simply write a cover. Here you can write, okay, this is not cover, rename, this is front glass. Similarly you can write here rename back cover. Here you can rename body, and this is nothing but your platform. Okay, so now you can, even here you can select all, right click, rename based on definition. So you can see like in image size for front glass, in image size for body, like that you can define this sizing. Okay, so I am not using that right now, so you can do at your end and you can define the respective sizing. Let's do the generate mesh. So what we are doing now, we are defining 3 mm size for the whole components. So now if you see, our mesh is performed. So you can see like this. Let's hide this body. Okay, you can see over here, right? So keep in mind always, when you are doing the explicit simulation, at that time your simulation time is greatly affected by your minimum element length. So how to find out that minimum element length? Characteristically, go to here. Here if you see the quality, yes, and here instead of mesh matrix, go to the characteristic length, and here go to control. So here you can see your minimum element size is 0.03. So let's display 0.3, update y-axis. Now if you see, there are so many elements where you will find your minimum element size as small as like this. You can even see here, right? This is the size of between 0.08 to 0.2. This will also, you can see the minimum size, right? So likewise you can do, you can check the minimum element length and try to increase this size as much as possible. So what we can do, let's see, let's hide body, insert, and insert method. Let's try to define multi-zone and try to use the hex mesh. Show all bodies, and here also hide clear generated data. Show all bodies. If you click over here, and let's hide this, let's generate the mesh. So what I did, I define the multi-zone for this respective body, and let's see if minimum L length will going to increase or not. Now let's see, reset 0.3, update y6. Okay, so now you still find that minimum element length for the few of the components. So if I can hide, here you will find that there are few elements which are having the minimum element length of 0.05 to 0.12. So you need to focus on that and try to increase this. Show all body, let's hide, hide, hide. Okay, so on these few elements you can either increase the size. So we had used multi-zone, and we had used the global size of 3. So if you make it 4 or 5, then definitely this element size will going to increase. Okay, suppose if you are not able to solve the simulation at for your workstation, then you need to focus on this respective point. At present I am keeping the same values, so I do able to solve that. Now let's do the next thing. Once your meshing is done, the next is to define your loading condition. So boundary condition we already defined, fixed as the ground, and now let's define the loading condition. So loading condition, there are two possibilities you can apply, as we are simulating drop simulation. So either you can right click, insert, you can either define the drop height, or insert, right click, and you can define the velocity. So let's talk about the first drop height. Inside the drop height, you will find the geometry you need to select. So consider box, select all geometry. You should have your three bodies, and here you can define, let's assume 1.5. So 1500 is our 1.5 meter is nothing but our drop height. So here you can even imagine that here you can define your local coordinates if you have created, and the direction. So accordingly you can see here meter per second. So basically here the respective velocity is calculated. Okay, now next let's talk about the other thing, like over here if you are going by drop height, you need to define the respective height, you need to model, and then it will take a longer time to perform this respective simulation. The best way is to make this as much as closer, calculate the respective distance and convert that into respective velocity. Okay, and you can define the respective velocity over here. Okay, by defining either by vector or component. So let's assume that I'm using like for example, let's use a 22, and here you can make it minus 22. Okay, now the object is moving, or object is dropping on this respective platform at a velocity of 22 meter per second. The actual height for a drop height, it's, you can see 1.5. It is calculated based on this respective coordinate 5.426. So you can see whether first you can perform for a drop height, and then you can perform for the velocity. For example, if you have, instead of cell phone, if you have other objects which are placed at different heights, you can calculate the respective velocity as we discussed in previous section, and then you can define that respective velocity inside this tab. Okay, and then try to simulate the respective deck. Okay, now once your deck is ready, then you can extract deformation, you can extract the strength like elastic plastic, can even elastic plastic, then you can check elastic strength. Once it is done, then you can extract the stresses, that is equivalent Mormon stress for the elastic material, and max principal and minimum principal for your brittle material. Max principal and minimum principal. So basically we are using a class, so you should use which is a brittle material. For that you can check the max principal stresses and minimum principal stresses. Okay, and then you need to solve the simulation. So likewise you need to perform the different steps which I discuss on this. It is quite simple as that, only the challenge is how to define the velocity and perform the meshing. Meshing is very important. You should keep the minimum element size as much as higher as possible in order to reduce the computation time. Okay, now let's try. You just right click and then solve the simulations. It will take longer time for the simulations, but I do already have the results. So assuming that the simulation is performed, now you can see over here. Let's discuss the result. Now let's see. So let's see further the first one, the deformation. So now if you see our deformation is 15 mm. So for the respective velocity, you can even see the animation. Let's do animation. So now it will going to show you the actual animation, how the drop of this respective cell phone is happening. So you can define your respective frames and respective time. Now if you see, let's have a close look on this. Right, you will find this drop is happening. Results, let's the without contour, you can even see without contour how it is deformed, this respective edge. for the respective velocities, and you can easily see that glass is broken, front glass is broken, or the crack is developed. Okay, now let's talk about the elastic strain. So you can hide this platform, hide body, and you should have some elastic strain, okay, on this plastic cover, and also you should have some plastic strain because this glass is brittle material, and then you should have some equivalent stresses. Let's hide the glass, okay, it just be visible probe, and you will find that in the range of 120 to 130. At the quarter it is 178, and the max principal also in the range of 209. You can see the max. Minimum principal is also there. So let's hide the body and check. Okay, so this is the actually the simplified geometry as well as simplified material. So in actual you will have different layers of material. You will have circuit, you will have toughened glass, you will have actual steel body, or whatever the body material is there. So like that you can model the different component, assign the different materials, you will have the different results. Okay, so now let's check further how the stress is deforming. Let's try to animate this also. So this is the true scale animation. You can see it will take time because we had given higher frame and higher time of 10 seconds, so that it will calculate and then it will display. So you can see how it is deforming. Okay, and also it is rebouncing. Once we had given the respective time, you can easily see that it is rebouncing also. See here, clash is happening. Okay, so this is all about your corner drop. So you can simulate according to this. And when you have a cell phone drop test, there you will find that different loading conditions or different component placement configuration are performed. So basically this is uh, right hand corner, you will also find the left hand corner, then you will also find this corner edge drop, then you will find the front face drop, this, and also you will find this front edge drop. I had already created two more models, so if I can show you over here, let's discuss the front face impact. So when you do have front face impact, you should have geometry parallel to this, like this, and then you are assuming that your cell phone is dropping on the front face, and it is having the impact of this toughened glass with the platform. So you can see through this if I can show the max principal, minimum principal. Okay, and there is one more important term which I need to define, which I forgot to mention. So let's discuss over here. So analysis setting. In analysis setting, you need to define the end time frame. So basically you need to think that how much time it will going to take for the full drop positions. So if you see, our drop is actually happened at a time of let's see, you can easily find out that even the energy sum recovered. So you can see here let's so you can easily see over here, this is what our kinematic energy, this is the internal energy. So always you should have such kind of graph. So your internal energy and kinetic energy should collapse. This point is nothing but your impact point, and after that this curve is as constant. So this hourglass energy, once your model is created, you have properly defined the boundary condition, properly mesh, then you should have minimum, as much as minimum, this hourglass energy. Neither it will create the unrealistic results. So basically you should have this as minimum as possible, this hourglass energy. So now if you see in our model, let's animate this further so that you will come to know where the impact is happening. So basically impact is somewhere here, and once impact is done, we are still carrying the results. So likewise you need to define the respective time frame. So it will always take time when you click on the animation button. So now you can see the animation is approximately, the impact is approximately at 2.5 raised to minus 4, and then further we are carrying the results. So now here in analysis setting, you need to define this according to your impact. So at present we consider 0.0015 second time frame. Okay, this is the important term when you are using this when you are simulating the explicit simulations. There are few more important terms like it should not go higher, but I think for present video it is not required. You can check our other explicit simulation video. There I had explained all this in a depth. Okay, and one more thing, like in output controls you can define this, like the result points, how many results points you want. So basically these result points, you can see all these result points. So we have mentioned the 50 result points. So accordingly it is, let's go to analysis setting. Here you can see the 50 result points, and the same you will find the results. If you want the more result point to be, you want to see the more smooth of draft, then you can further increase this respective result points. Okay, now let's go to our actual problem here. So if you see here how the impact is happening front face, now you can see it is dropping. Okay, now at this point the drop is happened and it is further rebouncing. Okay, so let's check the stress. Stress is 125 and all four corners have the highest stress values. Let's check the equivalent plastic strain further. You can hide this body. Okay, total deformation, plastic strain, equivalent strain, these are the important parameters to see the stresses. Okay, let's discuss one more thing. This energy summary, you see here the graph is not as smooth as this, so it means there is some issue in auto. This is just the assumption. So in actual you should have the completely cross, your internal energy should cross the kinematic energy. Okay, so based on that you can assume that your simulation correct or wrong. So this is the front glass, and then next is the another is, you will find here this corner impact, not corner but edge impact, side edge impact. You can assume this is side edge, this is front edge. So according to your nomenclature you can assume that. Now here also you will find the same. If I can display, let's animate this with the 100 frames. So once it is animated, let's see here, and here you will find only the velocity you need to define. You can define the respective velocity. Here I had considered as a 25 meter per second square, and all remaining boundary condition are the same, like fixed bound. This was you have body interaction, that is frictionless for all bodies. You have bonded interaction for all three bodies. Material also is like we define the material here, like aluminum alloy. For this structurality platform, your body cover is polyethylene and your front glass as a float glass. Same, only velocity you need to define like this, and your geometry should be rotated. I will explain you how to rotate a geometry. Now let's first discuss total deformation. Let's animate this. So you can now see, you are able, I think, how the impact is happen. Okay, so you can see this is a corner drop and then body slightly sliding, and then you will have the rebound. So if I can increase this as a 2, then you can see, right? So this is what the actual scenario when you will find that your side edge drop will happen. And for this you can even imagine the stress should act on this respective max principle, minimum principle. Okay, you can even check the equivalent plastic strain, elastic strain, and even equivalent plastic strain. So basically you will find the plastic strain for the glass. You can see when you use the tempered glass, there you will have a further more realistic result. See here. Okay, and let's hide cover and see the stresses. So basically it is on the back. Max principle is almost same as equivalent stress over here. 204 is the stress. So you need to compare this with the yield limit. Okay, and define whether your geometry is passing or failing. If it is above yield, then you need to do some design changes. If it is below yield, then you can say that it is acceptable and define the respective factor of safety. Okay, so this is basically all about your all three drop conditions. Now let's click on the geometry. I will explain how to rotate the geometry. So you can imagine if you have any questions related to this explicit, you can just comment me on the video. Don't forget to like and share this video. I will try give you reply as soon as I received your comments. Okay, so now if you wanted to save this animation, you can even save this animation from here. You can click over here and you can define in your respective folder. Just save it. There are 4 different parts like mp4, wmp, avi file, and even gif file. So likewise you can even save your animations. So now if you see, our geometry is open. Now in order to discuss how to rotate, and so let's assume you want to draw this edge. So for that, go to move, select the whole geometry, and rotate this geometry according to make it as right like 345. Enter. Okay, and then select further and try to rotate that whatever the angle you wanted to consider. Let's consider the 30-degree, right? And then you can make it as closer as the platform. Okay, so this is what you are the side edge impact, and just try to simulate the scenario. Furthermore, let's do Control Z, and in order to make it the front face impact, you can rotate whole and make it horizontal as possible. So like 60-degree I'm assuming, and then okay, I think this is not selected, so let's do Control Z, select whole the body, rotate along this, enter the 60-degree, and then select further, make it as closer to the platform. Okay, now you can see that this is created. Then further select the component, click on the top view, and then try to rotate as a 90-degree or 270-degree. Okay, now you can see that your front face drop is prepared. So I likewise you can rotate by using option move, and then you can simulate your respective solution. So first we discuss about the corner drop, then we discuss about the this is the corner drop, then we discuss about the front face impact, and then we discuss about the front edge impact. Okay, so that's it guys. Let me know your comments. I'll be there to help you. Thank you. Bye bye. Take care. Please don't forget to like, share and subscribe to our channel.